Okay, good evening, class. So in chapter 8, we talk about dental x-ray image characteristics. So some of the questions we'll be able to answer after this chapter are the following. What factors influence film density and contrast? What is the difference between short scale and long scale contrast? What factors will influence the sharpness, magnification, and distortion of dental x-ray image? And what X-ray beam angulation is required to minimize distortion in an X-ray image. So this starts on your dental radiography textbook on chapter 8, which is on page 72 all the way up to 79. So just note the page numbers on your slides may not match up exactly with mine, depending on which version you have. So just bear with me and try to follow along. All right, so we're going to be going over the overview of image characteristics as well as visual characteristics and geometric characteristics. So the purpose is to describe in detail the visual image characteristics of film density and contrast, to be able to define the geometric image characteristic of sharpness, magnification, and distortion, and also discuss how influencing factors alter these image characteristics. A dental radiograph appears as a black and white image or a picture with varying shades of gray. And in it, we have something called radiolucent imagery and as well as radiopaque. So in radiolucent images, the portion of the processed radiograph that is dark or black. So a structure that appears black on film lacks density. Whereas in a radiopaque image, this is the portion of the processed radiograph that looks white. So this is a structure that appears white on film and is dense because it absorbs or resists passage of the X-ray beam. So these terms are relative. For example, although dentin is more radiopaque than dental pulp, it is more radiolucent than the overlying enamel. So we can use extremes as a way of comparing the two. For example, an airspace would be more radiolucent or black because it's the least dense, whereas an amalgam or some type of metal filling or crown is extremely dense and would appear radiopaque or bright white. In order to ensure that these differences are noticeable, both contrast and density must be optimized. So dental radiographs must be of diagnostic quality in order for the dentist to provide proper quality care. So in order to do this, the x-rays that you take have to have proper density on contrast, they must have sharp outlines, and they must be the same shape and size as the object radiographed. So some of the visual characteristics that we'll discuss are density and contrast. Density and contrast are the two characteristics that influence the quality of dental radiographs. And it's important to know how to alter radiographic variables in order to change the contrast, density, and image detail. Okay, so density. The overall darkness of blackness of a dental radiograph refers to the density. So the relative transparency depends on distribution of the black and silver particles in the emulsion. So what does this mean? So the emulsion is what we see on the film, or the image that we see on the film. And the relative transparency of the areas on the image depends on this distribution or this kind of pattern of silver black particles. And this area of heavier deposits of this silver black particles represents a higher degree of density. So some of the influencing factors are milliamperage, operating kilovoltage, exposure time, and subject thickness. So if milliamperage is increased, the film becomes darker. If kilovoltage is increased, the film density increases because the average density of the X-ray is raised. If increasing the increasing the exposure time will increase the film density. If subject thickness is increased, the film density will be reduced. If PIDs are changed on a tube head, it's important to adjust the exposure time accordingly. A recommended maintenance schedule should be followed for the film developer because old solutions will compromise the quality of your films. Contrast is the difference in degrees of blackness between adjacent areas. A film that is a compromise between a high contrast and a low contrast is what we want to see. So the overall contrast is determined by film contrast as well as subject contrast. So film contrast is the inherent qualities of the film and the film processing, and subject qualities or subject contrast is the characteristics of the subject, so the thing that you're taking a picture of, that influence radiographic contrast. So a standard preset setting is commonly found to be 70 kVp coupled with 8 MA. When an X-ray machine has the above set has these readings, the only thing that can be altered is the exposure time. So low operating kVp represents high subject contrast with areas of black and white, and high operating kVp represents low subject contrast with many shades of gray. Some of the influencing factors of contrast include increasing the kilovoltage. So when you increase the kilovoltage, what happens is you increase the mean or average energy of the X-rays, and by producing higher energy X-rays. Also, more areas of varying tissue density are recorded on the image and appear as shades of gray. So if contrast is low, the radiograph will have many shades of gray, and if contrast is high, the radiograph will have very dark areas and very light areas. Remember, kilovoltage controls contrast. Another thing that will influence contrast is developer temperature, and an increase in developer temperature will result in an increased contrast. So a radiograph that displays short contrast is said to have high contrast due to the easily distinguishable areas of black and white. And a radiograph that displays long contrast is said to have areas of gray and low contrast. So the scales of contrast are the range of useful densities. Short scale contrast, which is high contrast, will appear with only two densities, black and white. And this occurs with the machines functioning at low kVp. And then long scale contrast or low contrast is when you have an X-ray with many densities, so many shades of gray. And this occurs with machines functioning at high kVp. All right, an aluminum step wedge can demonstrate short scale and long scale contrast. So what this step wedge is a piece of aluminum metal, and it has graduating areas of density. And the step wedge is used to demonstrate corresponding film densities and contrast scales. For example, a step wedge will reveal that radiographs taken at lower kVp will have higher contrast than radiographs taken with higher kVp. This is a little counterintuitive because you would think that higher kilovoltage would increase contrast, but this is not the case. Higher kVp results in lower contrast and vice versa. So we can see a picture of what this looks like on page 75 through 76, and then figures 8-5 to 8-6. So 8-5 is a picture of what a step wedge actually looks like. And then when we take an X-ray of them on figures 8-6, this is what that would look like. So some geometric characteristics include sharpness, magnification, and distortion. So a lack of sharpness can change a diagnosis dramatically. It might cause a problem to be undetected in an early stage when the prognosis would have been more favorable. So it's important to take nice, sharp x-rays. Magnification is also important, especially when measuring the length of the tooth during root canal therapy. So lots of times when we're referring to those files that we use in root canals, when we're trying to figure out just how far or how far to measure that file, a lot of the times we're going to refer to an x-ray, and this is when magnification is important. So distortion occurs when a radiograph is taken at a vertical angle that is greater than or less than necessary. And this would give an image that looks either stretched or shorter than it really is. So a stretched image is called elongation, and a short version of that x-ray is called foreshortening. These are things we do not want. Sharpness is the capability of the x-ray receptor to produce the distinct outlines of that object. A certain lack of image sharpness is present in every radiograph. This is called the penumbra. And we can kind of visualize what a penumbra looks like on page 77 on figures 8-7. Sharpness is influenced by three factors: focal spot size, film composition, and movement. Film speed may affect sharpness due to the different sizes in silver bromide crystals. So the faster the film speed, the larger the crystals. All right. A penumbra. So what is a penumbra? The penumbra is that fuzzy or blurred area that surrounds an image. And then some sources of movement. So if we have the patient could be moving around, the film might be moving around, or even the x-ray unit itself can be gliding or floating, and that can move around. So that's part of the movement that would cause a loss of image sharpness. And then the film composition. So we have the emulsion of faster film that contains larger crystals that produce less image sharpness. So in a faster film, like an F-speed film, it's going to have larger crystals, and that's what's going to allow the image to appear with less exposure time, but it's also going to produce less image sharpness. And with focal spot size, the smaller the focal spot, the sharper the image will appear. Magnification results from the divergent paths of the X-ray beam as they radiate from this focal spot. So remember when we talked about the flashlight pointing against the wall, the divergent paths is sort of like what happens with that, with the flashlight or the area of the wall that's illuminated by the light. So as you pull away from the wall, the area of illuminated wall will grow bigger. So, and this is what we're talking about with magnification. So some of the influencing factors are the target receptor distance. So a longer PID, the target receptor distance, so the distance from the target to the receptor. And a longer PID and target to receptor distance results in less image magnification. And then we have the object to receptor distance. So this is whatever we're taking a picture of, the distance from that all the way to the receptor, which is your film or X-ray sensor. And an increase in this will result in an increase in image magnification. So a longer PID results in less image magnification and vice versa. And the closer the film is to the tooth, the less image enlargement there will be on the film. So distortion is a variation in the true size and shape of the object being radiographed. This results from unequal magnification of different parts of the same object because of improper receptor alignment or angulation of the X-ray beam. For example, if we have a film that we are mounting in or we are placing in a patient's mouth, and that film becomes bent, because of this, you will have something called distortion. Two of the influencing factors are object to film alignment and X-ray beam angulation. So in object to film alignment, the object and the film must be parallel to each other or there will be distortion. In X-ray beam angulation, the X-ray beam must be directed perpendicular to the tooth and the film. So this is that whenever I talk about everything needs to be parallel. So the film needs to be parallel with the tooth, and the tooth needs to be parallel with, if you look at the side of the X-ray cone, it's going to be parallel with that, but it's actually going to be perpendicular with the X-ray beam. And a distorted image may appear too long or too short. All right, that's it for chapter 8. Thanks for listening, and we'll see you next time.